All right, in 7.1, equivalent forms of exponential equations, right at the top, you have a little investigation. It represents bacteria growth in a petri dish. And basically, if you work from left to right, in the top row, you see that if you start with, well, 4 to the power of 0 is 1. Anything to the power of 0 is 1. And then on the day that you put in 4 bacteria into this petri dish, you have 4 bacteria. And then the next day, you have 4 squared, which is 16. And then how many would you have the next day?
We're looking at the graph or the chart?
Yep, the table at the top. So you've got 1, then 4, then 16. How many would you have on day 3? You don't have 4 to the power of 3 memorized?
It's kind of whack. So on 1, it's 64 squared. On the other one, it's 16 cubed. They're both the same thing, but they're represented differently. Like if you draw them out, you have 2 completely different structures. I thought really hard on this.
Yes, you could have 2 completely different structures. So if we go to our next row,
they have the same value.
which we start with a base of 2, and we still have a n in the exponent, but before we use it, we're going to multiply it by 2. We end up with the same numbers. And what we end up with is 2 to the power of 6, which is 64. What's the point of this? It's just showing us that we can express powers in different forms without changing the value of the power. And it's often helpful to do so. So if you wanted to simplify this situation and you didn't want to deal with 2n every time, well, you could express it as 4 to the power of n instead of 2 to the power of 2 times n. And that would be fair. What happens a lot now and what we're going to be doing is we're going to be taking a number like 4 and trying to compare it to a log with a base of 2, in which case we kind of want to express our 4 as 2 to the power of 2. So you can express them in different ways. It's just a small example of what we're kind of looking at in the next, in this lesson. So a little bit of room for notes directly underneath that table. Basically just exactly what I said. Exponential functions can be represented. Exponential functions can be represented in many different ways. It is often useful to express using a different base. It is often useful to express using a different base. Good. Carrying on to example 1. In example 1, we're just changing the base of the power. So we're expressing in terms of a power with the base of 2. So in every single one, we want the final result to have a base of 2. Okay? So we're looking at A. You don't have any written there. Just to give you a heads up, there's going to be 4 of them. Start with 2 short ones, and then it gets a bit longer. A is the number 8. Can we express 8 as a power with a base of 2? Short answer, yes. What would it look like? 2 to the power of?
3.
2 to the power of 3. Why? Because 8 is the third power of 2, right? You go 2 times 2 is 4, times 2 again is 8. So you need 3 factors of 2, and you've got 8. Second one is 4 to the power of 3. And we want to express that as a power with a base of 2. So this is just like the warm-up that we did. All you need to do is express 4 as a power with a base of 2. In which case you have 2 to the power of 2 to the power of 3. Okay, so step 1 is write 4. If you're doing the little side notes here, write 4 as 2 to the power of 2. And now what are we going to apply? Which law? Power law. Good job. Or power of a power, sorry. Power of a power. Law of exponents, in which case we multiply the exponents together, which gives us 2 to the power of 6. 2 to the power of 6 has the exact same value as 4 to the power of 3. C gets a little trickier here. We have the square root of 16 times the 5th root of 32, and that raised to the power of 3. So again, the square root signs can look a bit awkward. We don't want to deal with them in that form. Maybe square root of 16 you can just do off the top of your head and you reduce it to 4, and then you can work from there. What we're going to do instead is get us down to a base of 2 as quickly as we can. In order to do that, we're going to write the radicals, in exponent form. So the square root of 16 becomes 16 to the power of 1/2. And this one is a little bit interesting. Basically what you would have is, and I can write it in 2 steps. You would have, I'll write it in 2 steps off to here, but basically it would turn into 32 to the power of 1/5 inside the bracket to the power of 3, which is then 32 to the power of 3/5. Yeah? So that's what we have.
But I have a crazy idea.
Yep.
32 is 2 to the 5, right? So you can just do the 5th root of 2 to the 5. Then the 2 5s cancel out, and it's just 2 cubed.
Yes,
Okay, sweet.
that is correct. That's where we're going to get to. Yep, so again, another way you could do this is just right away express 32 as 2 to the power of 5. Then you have 2 to the power of 5 to the power of 1/5. They'd cancel out. 2 to the power of 1 to the power of 3 would be 2 to the power of 3. Good. Let's keep on going this way. So now at this point, we're going to express everything with a base of 2. Express powers with a base of 2. So 16 is actually what? 2, 4, 8, 16. 2 to the power of 4. So we've got 2 to the power of 4 to the power of 1/2 times 2 to the power of 5 to the power of 3/5. And again, as you're doing this as practice problems, you can knock off some of these steps that are a bit easier. So this 4 times 1/2 is 2 to the power of 2. Multiplying that by 2 to the power of 5 times 3/5 is just 3. So we've got 2 to the power of 3. And now if we're multiplying powers with the same base, we actually just need to add the powers. Okay. That's the product law of powers, I think it's called. At any rate, we end up with 2 to the power of 5. Could we have gotten there without a few steps in between? Probably. But that's one way of doing it. The last one is a little bit trickier. And what the last one shows us is that any number can be written as a power with a base of any other number, okay? So it's going to look like it's never going to work, but it is actually going to end up working. Am I good to erase this? I'm clearing this.
Yep.
So D, the last one there, is the number 12. Our goal is to write that as a power with a base of 2. And you say, well, 2 times 2 is 4, times 2 is 8, times 2 is 16. I skip right over 12. So I can't actually do it, okay? So what we actually need to do is solve the equation 2 to the power of, we'll call it k, equals 12. That's what we're looking for, right? We want to express 12 as a power with a base of 2. So let's just make up the exponent. We'll call it k for now. And now our goal is to solve this. Okay, do you have any tricks that allow you to solve for k?
Log 2 over log 12? No, log 12 over log 2.
How about we start by taking the natural log of both sides?
Okay.
Okay, so take, not natural log, sorry, common log. Natural log is something different. Common log is base 10. Take common log of both sides. So I have on the left the log of 2 to the power of k. And on the right I have the log of 12. Why did we do that? What can I now do on the left-hand side?
Well, we can just put k log 2 instead of log 2 to the
Okay,
k.
so we can apply the power law of logarithms. Power law of logarithms allows me to take the exponent of our log and bring it out in front. So on the left-hand side, now I have k times the log of 2. That equals the log of 12. And now basic algebra to solve for k, I can just divide both sides by the log of 2. Which tells me that k is the log of 12 over the log of 2. Therefore, 12 can be written as 12 equals, with a base of 2, 2 to the power of k, we said, right? And k is the log of 12 over the log of 2. So up here in our exponent superscript, we have a bit of an awkward statement, but it's true. And this strategy will allow you to rewrite any number as a power of any other number. Okay? Take the log of both sides, apply the power law of logarithms, solve for k, put that up there in the exponent, done. This, take the log of both sides, that step, it's going to come up again and again. This step you should be fairly familiar with to bring down the exponent of the log. And if you chuck that in a calculator, if you type that into a calculator, you would get 12. Just if you wanted to confirm or double check. Okay, so what do we learn from this? If you have a little bit of space for a note right at the bottom of that page, then you can write it there. If you don't have space, then write it somewhere else on that page. But the note is what I've been saying. Any positive number can be expressed as a power of any other positive number. Any positive number can be expressed as a power of any other positive number. Okay, in example 2, we're going to use the tools that we just learned for changing the base of a power in order to solve problems. Okay, so example 2a, we have 4 to the power of x plus 5 equals 64 to the power of x. This one is not super difficult based on what you know about logs and exponents. What can you do here? What could you do here? Do you see any connection between our bases?
Well,
Okay, we're going to express 64 as 4 to the power of. You have it memorized now. 4 times 4 is 16, times 4 is 64. Okay, so in our next step here, the left side hasn't changed. It still has an exponent of x plus 5. But over here, we now have 4 to the power of 3 to the power of x. Which our next step is pretty easy. We apply the power of powers law, and we get 4 to the power of 3x. Okay, this is apply power of power law of for exponents. And now it's pretty straightforward. If you have 4 to the power of something and it's equal to 4 to the power of something, what does it tell you about those exponents? The exponents also must be equal. Okay? So what you can actually do is now just take x plus 5 equals 3x. Let's just put a note there so that we remember exponents must be equal. Okay, another way to say that is equate the exponents. If they both have the same base and the expression on the left is the same as the expression on the right as equivalent value, then the exponents must be equal. Well, from here, you just use basic algebra to solve. Okay, so I would, subtract x from both sides. That would leave me with 5 equals 2x. And then divide both sides by 2. That would leave me with x equals 5 over 2. Second example and final example is 4 to the power of 2x equals 8 to the power of x minus 3. This one is slightly trickier, but again, you're going to look at both bases and you're going to see if you can express each of these as a power with the same base. So your immediate thought is, oh, maybe I can use 4 because it's the smaller number, but then you realize that it's 4 times 2 is 8. I can't actually express 8 as a power of 4, but there is a number that I can use.
so we use 2 as a base.
So we use 2 as a base. I'm going to try to skip a couple of steps here. So we're going to end up with 2 to the power of 2 to the power of 2 times x, which is going to give us 2 to the power of 4x. On the right, we're going to end up with 2 to the power of 3 to the power of x minus 3. I'll write that one because it has an extra step in it. So we've got base 2, then we've got 3 x minus 3. Now, if you can do this part in your head in one step, go for it. But all I wanted to point out is that we have to remember we're now distributing that 3 to both of the pieces of this binomial. And we can equate our exponents because they both have the same base. So we've got 4x, 2 steps in one here, is equal to 3x minus 9. Now I can solve for x by subtracting 3x from each side. X equals -9. It's a combination of your logarithm and exponential laws. This lesson is just exponential. So it's a combination of your exponent laws and basic algebra that allows you to reduce and solve. The big step that we learned in this one is from here to here, equating your exponents as long as they have the same base. Okay, practice problems are there for you on the bottom of the page. Enjoy.